The National Map is a collection of mapping products and services produced by the USGS National Geospatial Program. The products and services are accessed via the Internet through service calls and graphical user interfaces. The National Geospatial Program has released a series of how-to videos for people who are working with the National Map data and services. The videos show how to use the services and interfaces to access data and tools for viewing, analyzing, and printing geospatial data. The training materials are a mixture of video and PowerPoint-based lessons. Lessons 1 and 2 serve as an introduction to the training materials. The remaining lessons are designed as quick how-tos and may be viewed as needed in any order, depending on the user. Lesson 10b3, Clipping LAS Data and Creating Derivative Products in ArcGIS Pro. Lessons 10b1 and 10b2 introduce the basics of interacting with lidar point cloud data in ArcGIS Pro. This lesson will cover creating and editing a shapefile as an area of interest, creating a LAS dataset, and generating derivative data in ArcGIS Pro. If necessary, please review Lesson 10b1 for guidance with importing LAS files, filtering, and visualizing lidar point clouds in ArcGIS Pro. Any use of trade, product, or firm names is for descriptive purposes only and does not imply endorsement by the U.S. government. By the end of this lesson, you will be able to create and utilize a shapefile area of interest to subset LAS files, create a LAS dataset with multiple LAS files, generate and export raster surfaces and contours derived from the lidar point cloud, and visualize the data in a 3D scene. In this tutorial, we are using uncompressed LAS data, but the National Map also offers compressed LAS data, which can be converted to LAS files for compatibility with ArcGIS Pro. Refer to Lesson 10E2 on using LAS zip to decompress lidar data. If you're interested in learning more about using USGS lidar data in other software packages, additional videos show how to use lidar data in Global Mapper and LP360. For this lesson, we will be using the same tiles of LAS data from Lesson 10b1. If you have not done so already, please download the USGS LPC CO SoPlat River Data for Lessons.zip file from our Rocky website at rockyweb.usgs.gov/training_data. After you've downloaded the lidar data, extract the zip file into a folder on your local computer to use during this lesson. The National Map has a download client where you can find USGS products, including elevation data such as lidar point clouds, at apps.nationalmap.gov/download. If you are interested in learning more about downloading products on the National Map, be sure to check out our training videos located at www.usgs.gov/ngp videos. This lesson uses ArcGIS Pro version 2.5. To begin, open ArcGIS Pro on your computer. Launch ArcGIS Pro. Use your enterprise or personal login information if prompted by the ArcGIS Pro login prompt. Open a new map. Name the project ArcGIS Pro LiDAR Training Lesson 10b3. Use the same folder we downloaded the lidar data to in the previous lesson 10b1. Then click OK. Depending on your ArcGIS Pro version, the basemap may vary. This exercise specifically uses ArcGIS Pro version 2.5. However, any version 2.1 or newer should suffice for this tutorial. ArcGIS Pro versions older than version 2.5 may default to different basemaps other than the topographic basemap. To change the basemap, navigate to the Map tab on the Layer ribbon. Under the Layer section of the Map tab, click the Basemap drop-down arrow and select the Topographic Basemap option. Under the Map tab on the Layer ribbon, select the Add Data button. In the Add Data window, browse the location of the lidar point cloud LAS files that were downloaded from the FTP site. Highlight the 6 LAS files and load them into your map. Under the View tab, open the Catalog pane. Expand the Folders drop-down and right-click on the project folder and select New. Click on Shapefile. In the geoprocessing pane that appears, accept the default folder location. Under Feature Class Name, call the shapefile lesson 10b3 AOI for our area of interest. Change the geometry type to polygon if necessary. Change the coordinate system to NAD 1983 UTM Zone 13N. You can do this by searching in the Coordinate System pop-up window, or you can select an existing layer in the drop-down menu which should have the same coordinate system. Accept all other defaults. Click Run. The empty shapefile will be added to the table of contents, but we still need to draw the extent and shape of the polygon. Click on the Edit tab and under the Features ribbon, select Create. The Create Features pane will open, and under Templates, select 10b3 AOI from the list. Select the polygon icon to draw the shapefile using vertices to create the polygon. We want our area of interest to be everything east of the foothills. Using the topographic map and the contour lines, left-click at the center of the top left last tile, beginning at the base of the foothills. Left-click again at the bottom of the middle tile and trace the tile extents to include the last tiles east of the foothills. Double-click to finish drawing the polygon. To save your edits, under the Edit tab, select the Save icon in the Manage Edits section. Click Yes in the dialog window to save all edits. In the Table of Contents pane, select the default symbology rectangle under Lesson 10b3 AOI layer. This will bring up the Format Polygon Symbol window in the Symbology pane. Select the black outline 2-point thickness. Now is a good time to save your project. Now that the AOI is clearly defined, we can create a LAS dataset constrained by the extent of our AOI. A LAS dataset is designed to use LiDAR data in .las or .zlas file types. It supports any LAS file version 1.0 through 1.4. It is important to note that the LAS format supports the classification codes for each point according to the American Society for Photogrammetry and Remote Sensing, ASPRS. And ArcGIS applies the class code specified for LAS version 1.4. A LAS dataset has the capability to store and reference many LAS files, compiling them to one LAS dataset, similar to a mosaic of raster surfaces. The LAS dataset refers to the LAS file or files in their native binary format of stored airborne LiDAR data. By using a LAS dataset, users can more efficiently conduct QA/QC on LiDAR data and quickly visualize many LAS files at once, as either a tin or point cloud, in both 2D and 3D views in Esri software. The LAS datasets calculate statistics for referenced LAS files in order for the user to understand and analyze the LiDAR data. By using a LAS dataset, we can create raster surfaces and derive products to better understand the topographic layers from the LiDAR point cloud. For more information on what a LAS dataset is, or LAS dataset capabilities and properties, visit the ArcGIS Pro help pages listed here. Open the Tools Geoprocessing pane in the Analysis tab and search for Create LAS Datasets. For the input files, browse to the 6 LAS files downloaded from the Rocky website. Select all 6 LAS files. Name the output LAS dataset lesson _ 10b3 _ AOI.LASD. Surface constraints can be used to limit the LAS dataset to a given extent. Using our AOI shapefile, we will clip the LAS dataset to the AOI's extent. Under Input Features, select lesson _ 10b3 _ AOI from the drop-down menu. There is no height field, so leave it blank. For the type, we will use a soft clip to define the boundary of the dataset. Select NAD 1983 UTM Zone 13N /NAVD 88. Check the compute statistics if not already marked, then click Run. ArcGIS Pro allows various surface constraints depending upon the feature class or shapefile type. Surface constraints use the feature's geometry to capture or define a surface when it is displayed in a tin format. Esri defines options with hard or soft designation, which refer to whether the surface edges represent distinct breaks in slope or a gradual change. Anchor points can be used for point data, and hard or soft line constraints are typically used for break lines to delineate water bodies or linear features. Hard clips and soft clips are used to delineate a boundary of the LAS dataset. Surface constraints are applied only when the LAS dataset is drawn as a surface. If the LAS dataset is drawn using points, it will draw all LAS files being referenced in the LAS dataset. For more information on storing LAS datasets or LAS files and surface constraints, visit the Esri help page shown here. In order to better view the new LAS datasets, we will convert the map to a local 3D scene. In the View tab, select Convert and click Local Scene. This local scene shows 2D layers draped over a 3D scene and draws 3D layers that can be extruded or exaggerated to show perspective or represent elevation data. After you've converted the map layout to a local scene, save your project by clicking on the Save icon at the top left corner of the ArcGIS Pro window. In the 3D rendering of the LAS dataset, make sure the LAS dataset layer is highlighted and click on the Appearance tab under the LAS Dataset layer ribbon. Click on the Symbology icon, and in the Symbology pane, click on the yellow pyramid to draw the layer using a surface and choose Elevation from the drop-down to visualize the dataset in the AOI. Make sure that the Draw Using box is checked. The LAS dataset will only show the clipped extent when it is drawn as a layer surface rather than a point cloud. You can see the noise and artifacts represented in the LAS dataset because all classes are turned on using the elevation field. We will change the LAS points filter to only ground points. Right-click on the lesson 10b3 _AOI.LASD from the table of contents and select Properties. In the Layer Properties window, select the LAS Filter tab. As you can see, all the classification codes are turned on and currently drawn in the map view. Uncheck the All box under the Classifications code to turn all the classes off. Then check only the toGround class and click OK. Now that we have filtered only the ground points, we can create a digital elevation model, or DEM. In the Analysis tab, open the tool's Geoprocessing window. Search for LAS Dataset to Raster. Select the LAS Dataset to Raster Conversion tool. The LAS Dataset Conversion to Raster tool uses interpolation methods to generate a smooth output of raster cells. The two interpolation types for this tool are binning or triangulation. Binning is typically faster and assigns values based on points within the extent of the cell. Binning does not fill voids or data gaps, but allows options for filling these gaps. Binning gives various cell assignment types such as average, nearest neighbor, inverse distance weighting, and other statistics to define the value of the cell based on the points binned to that cell. Triangulation uses interpolation of the points to create a triangulated surface of the LAS dataset. The interpolation method can be either natural neighbor or linear, and point thinning can be used if needed. In the Geoprocessing window, select the lesson 10b3 _AOI.LASD file for the input. Name the output raster DEM _10b3 _AOI. We will use triangulation with natural neighbor interpolation and no thinning. Make sure the data type is floating point and that cell size is selected from the Sampling Type drop-down menu. This LAS dataset references QL2 level LAS files, giving a nominal point spacing of 0.7 meters or better. It's a good practice to never use a resolution finer than the point spacing. We will use a resolution of 2 meters for the DEM. In the Sampling Value section, write 2, then click Run. This may take a minute or two. Once the tool has finished running, save your work. We will now create more derivative products from the DEM that was generated. Select the DEM underscore 10b3 underscore AOI layer from the table of contents. Click the Analysis ribbon and click the Raster Functions dropdown. Select Raster Functions from the dropdown and then expand the Surface dropdown and select Hillshade. Choose the DEM underscore 10b3 underscore AOI layer for the raster input section. For this tutorial, we will keep the traditional hillshade at 315 degrees azimuth and 45 degree altitude. Accept the remaining defaults and click Create New Layer. Reorder the DEM layer in the table of contents to be on top of the hillshade. Under Appearance, make the DEM 50% transparent and choose a color scheme from the Symbology tab that fits your liking. Now we can visualize the final DEM more clearly in the 3D view on top of the hillshade layer. Next, we will create a digital surface model. A digital surface model, or DSM, is similar to a DEM. However, it shows the maximum heights of objects above bare ground, such as tops of trees and buildings. Right-click the LAS Dataset in the table of contents, and in the Layer Properties, under LAS Filter, check All. Then uncheck classes 7 Low Noise, 11 Roads, and 18 High Noise. These classes contain some misclassifications in the high noise class and will show artifacts and unwanted noise points in our DSM results. Once the points are filtered, open the geoprocessing pane and search LAS Dataset to raster. In this case, the tool is still open from the last time it was run. Select the tutorial 10b3 underscore AOI.lasd file from the input dropdown. Name the output raster DSM underscore 10b3 underscore AOI. Select elevation for the value field and choose binning, maximum, and linear for the interpolation fields. Make sure the sampling type is cell size and type 2 for the sampling value or resolution. Click Run. We'll create a hillshade for the DSM using the same methods for the DEM hillshade. Once you have your DSM raster created, highlight the layer, click the Analysis ribbon, and choose Raster Functions. Expand the Surface dropdown and choose Hillshade. Select DSM underscore 10b3 underscore AOI from the input dropdown and choose Create New Layer. You may edit the symbology and transparency to view the DSM over the hillshade. You can also set your DSM to your preferred color scheme. By comparing the hillshade layers created from the DEM and the DSM, the surface features become very evident. Turn off the DEM and the DSM so that only the hillshade layers are visible in the map window. Order the hillshade layers so that the DSM hillshade layer is above the DEM hillshade layer. The swipe tool only works in a 2D map, so we will need to convert the 3D scene back into a 2D map. Click the View tab and select the Convert drop-down arrow. Choose To Map. Once the 2D map has been generated, make sure the hillshade DSM 10b3 layer is on top of the hillshade DEM 10b3 layer. Zoom into an area that seems densely covered in trees and buildings. With the hillshade DSM 10b3 layer selected in the table of contents, select the Appearance tab and click on the Swipe tool. Click and drag the Swipe tool up or down or side to side to visualize the differences in the DSM and DEM hillshade layers. When finished exploring the differences, close the 2D map window and return to the 3D scene. It's important to note that the hillshade layers were not saved as individual rasters to the project folder. Rather, they are currently referencing the source layers as either the DSM or DEM. We will need to export these layers to save them as individual hillshade rasters. Right-click the hillshade DSM 10b3 raster. Select Data and then Export Raster. Accept the default name and location. The cell size should be the same as the source raster, 2 meters by 2 meters. Accept the remaining defaults and click Export. Repeat the same process for the hillshade DEM 10b3 layer. Now is a good time to save your project. Now that we have created elevation models for both the bare earth ground and the surface features, we can use map algebra to determine the actual heights of various features across the area of interest. A digital height model, or DHM, can be created by subtracting the bare earth raster DEM from the DSM, showing the true heights of objects relative to the ground. Open the Analysis tab and click on the Tools Geoprocessing icon. Search for Raster Calculator and select the Raster Calculator Spatial Analyst tool. Double-click DSM_10b3_AOI, the minus sign, and DEM_10b3_AOI, or you can type the following expression: double parenthesis DSM_10b3_AOI, double parenthesis, space, minus sign, space, double parenthesis, DEM_10b3_AOI, double parenthesis, in the map algebra expression window. Name the output raster DHM_10b3_AOI. Click Run. Turn off all layers except the DHM10b3 raster. Change the symbology of the DHM10b3 raster layer to the Inferno color scheme in the Appearance tab. Under the Map tab, select the Explore icon. Navigate to the circular buildings in the north edge of the AOI. By clicking on the brightest part of the building, a pop-up will show up containing the pixel's height value. You can determine heights of any object by clicking on the pixel in the DHM10b3 layer and reading the attributes in the pop-up window. This building is approximately 40 meters tall. ArcGIS Pro has numerous pre-selected surface derivatives that are saved under the Data tab in the LAS Dataset layer ribbon. Deselect the DHM and turn on the lesson_10b3_AOI.LASD layer in the table of contents, then select the Data tab from the LAS Dataset layer ribbon. Click the Surface Derivatives drop-down arrow and choose Contours. Before running the Contour tool, we must filter out all lidar points that are not the ground. With the lesson_10b3_AOI.LASD layer selected in the table of contents, select the Appearance tab from the LAS Dataset layer ribbon, click the LAS Filter icon, and filter only the to ground classification. Go back to the Geoprocessing window and name the output feature class Contours_10b3. Enter 10 for the contour interval. The map units are in meters, so we will have a detailed contour feature class for every 10 meters of change in elevation. Enter 50 for the index interval. This will show an index contour for every 50 meters. Click Run. The contour feature class we created is stored in the project's geodatabase. We will alter the symbology to view the contour lines and the index contours. Turn off the lesson_10b3_AOI.LASD layer. Right-click the Contour 10b3 feature class in the table of contents and select Symbology. Under the primary symbology header, choose Unique Values from the drop-down. Change Field 1 to Index Contours. The index contour function in the Contour tool created a binary output for each contour feature. 1 means that it was an index contour and 0 means it's not. Click on the line for the 0 attribute. If necessary, click the Properties tab to adjust the line color and line width. Choose a dark color for the 1 index contour and a lighter shade for the 0 contour lines. For this tutorial, we will use the medium coral light with the line width of 1 for the 0 value contour, and Tuscan red with a line width of 2 for the 1 value index contour types. Now we can clearly distinguish the index contours from the other contour lines. Save your project and close ArcGIS Pro. Congratulations! You finished Lesson 10b3, Clipping LAS Data and Creating Derivative Products in ArcGIS Pro. In this lesson, we discussed how to create and utilize a shapefile area of interest to subset LAS files, create a LAS dataset with multiple LAS files, generate and export raster surfaces and contours derived from the lidar point cloud, and visualize the data in a 3D scene. If you are interested in learning more about using lidar data, please see the additional USGS lidar training videos in ArcGIS Pro, LP360, and Global Mapper at usgs.gov/ngp videos.